now we are going to start with the fourth step of metallurgy. See, we have already completed the concentration, we have already completed we have converted our concentrated ore into oxidized form, we have already reduced that oxidized form, and now we have reached on the fourth step, which is a crucial step, because in this step we are going to convert the crude metal into the pure metal, right. That is what we did all the steps just for this main step, right. So how to do the refining now first you should know that what is refining actually. So refining is conversion of crude metal into a pure metal, right. So that you can just bring it from the market and just make it use in your any task wherever you require that. So in refining we employ various methods depending upon the different properties. I have some few methods for you. So the first method is distillation. This method actually is based on the property that, or you can say it is used for the metals which have low boiling point. So the condition required for this method to be employed is that the metal which is present along with the impurities, that metal should possess the low boiling point. So see how we are going to do this distillation. This is my distillation flask, a round bottom flask, as you can see. This is a wire gauge, this is a burner I have kept, and this is my stand. This is a tube which is going to leading to another beaker, and here I have a condenser. I'll write here. Here I have a condenser. Again, this is my round bottom flask, right. This is my thermometer just to check the temperature, like up to which level the temperature is being raised. This is my stand. This is my wire gauge, because I cannot do direct heating, you know that. This is my Bunsen burner, right, and this is my metal impurity mixture. You must be thinking that we are doing refining, so what kind of impurities do we encounter with the metal? So you know that the impurities that must be present, that can be present along with the metal is mainly you can say metal oxides, can be a silicon, phosphorus kind, or any foreign substance. So these are actually three kind of impurities which need to be separated. So that is why we are employing this fourth step, that is the refining. So see, in distillation how we are going to separate them. The condition required is obviously that the metal should possess the low boiling point. So what I am going to do, I am going to take a metal and impurity mixture in this flask and I am going to heat it, right. As our metal possess low boiling point, so that means it will boil at the lower temperature. So let's see that, let's say that this black one is our the metal, right, and red one are the impurities. So the metal will just vaporize, and as these vaporize, they rises and pass through this tube, and on passing this tube they get condensed actually, because this is a condenser outside, and likewise we can collect our metal here. That means the vapor are getting condensed. So, but what about the impurities now? So, the impurities actually possess the boiling point high as compared to the metal. So, they will remain here, and we need to keep check on this thermometer. That is why we have put this thermometer inside, so that the boiling point must not be rise so much, because if the boiling point will exceed a certain limit, then the impurities may also form a vapor and they also pass along with the metal into a condenser, and we won't be able to separate the metal and the ore, right. And we want our metal to be separated from the impurities, so we need to keep check on the the temperature, right, obviously, and so that the metal just vaporize and metal just pass through this tube, get condensed and get collected into a beaker. So this is my pure metal. This is my pure metal, right. So you have to keep in mind that it is employed for the metal which has the low boiling point. Second is the liquation method. This method is actually employed for those metals which have low melting point, So now what we are going to do is again, you know that we have this red one is my impurity and this black one is my metal. So I am going to pour this mixture over this slope, as you can see, and we are constantly heating this metal. As the metal possesses the low melting point, so it will just melt out, right, and it will start flowing into the beaker. But as the impurity possesses melting point high as compared to the metal, it will not melt at the temperature and it will stays behind. It will stay actually behind, and the metal, this black one will just melt out and just get converted into a beaker, and we can just separate it, and this is our pure metal as a result of liquation. But you have to keep in mind that when you are doing it, then what condition is required actually is that the metal should possess the low melting point. This is a specific condition which is to be seen. The third step is the zone refining. You know that actually this step is used for separating those impurities which can be separated actually in a molten state. So I'll just write it for you. So zone refining is required to separate impurities in molten state. So what I am going to do here is, I am going to convert that metal with impurities in a rod kind of forms, as you can see this, right, this green one. This is my metal with impurity mixture converted into a rod form, right, and this is my a circular heater. This is my circular heater. So what I am going to do here is, I am just going to, and you know that there is a specific property that this circular heater is movable actually. This circular heater is movable. So what I am going to do here is, I'll just make this circular heater enter into this, and what happens as it enters into it, it actually melts the impurities. It actually melts the impurities. That means the impurities change into a molten state. And as I told you that this heater is movable, so as I will move it along the length of the rod, all the impurities will, this molten material even will flow along, and all the impurities which are present here, here will start melting out, and they will just move along the heater, and the time we reach the end of the rod, all the impurities, as you can see these red dots, right, these red dots indicate my impurities. So these impurities get collected at the end of the rod, and what I can do is to get rid of it, obviously I'll just cut it out so that our metal gets purified, and this rod is actually our purified metal now. Right. So by this method we can do it, but again you have to keep in mind that when we are doing zone refining, we have to keep in mind that it is employed for the metals in which the impurities can be extracted in a molten state. Right. So we are just left with another method, that is the fourth one, and what is that? Is electrolytic refining. You know that the basic principle actually behind the electrolytic refining is same as of the electrolytic reduction, because they both involve actually electrolysis, and you know that what is electrolysis. It is the you can say when you pass electric current, electrolyte, a substance has the ability to dissociate into ions. This is what is happening here. But you know that what is the difference between the reduction and the refining? When we are refining, we have to take care of that like in the reduction, like when we did reduction, we made cathode of carbon lining, and although we made anode of carbon rods, right? But in this case, when we are doing refining, we need to make anode and cathode with the separate substances. Just look at the board, it's a very crucial point in electrolytic refining. So in this, what I am going to do is, obviously I am going to take cathode and anode, because if in the absence of electrode, no electrolysis take place, you know that. So this is my cathode, and you know, like the material which is used to make pure this cathode is pure metal. So we need to take a block of pure metal in order to make a cathode. Now what about anode? Obviously we will be taking an anode of the impure metal, that is the metal with impurities. So it is made as anode. They both are connected to the battery terminals, because we know that we need to have a source of current here, and they will just help in distributing this current in the electrolyte. And this is my electrolyte, that is again a substance which has the ability to dissociate into ions when the current is passed. So now what is going to happen here, I'll just take an example in order to illustrate. So let's refine copper with this. Let's refine copper with this. So my impure copper metal is impure, I'll write impure with impurities as anode, right? And my pure copper rod is cathode, dipped into electrolyte. I'll be taking an electrolyte, a metal salt solution. Let's say I have CuSO4. I've already wrote it for you. So let's say it is our CuSO4. So what is going to happen, or what kind of changes I'm going to see, and you can say that how the refining is taking place. Just look at the board carefully, right? So what happens when I pass the electric current? Obviously the electrolyte has the ability to dissociate into ions. So it will just get dissociated, forming Cu2 positive and the sulfate ions. Now what happens, as we know that this anode is also made up of impure copper. So the reaction that will occur at anode will be copper will start losing electron and will form the copper ions. That means somehow the oxidation is carried out. Now these Cu2 positive ions, which is formed as a result of oxidation, will move into the solution, and in solution, as I told you, there are already present Cu2 positive ions. So these Cu2 positive ions will migrate to a negative terminal, that is the cathode, and here the reduction is going to take place. They will take up their lost electrons and form a copper. And you know that the weight of the cathode will keep on increasing, because here the metal is getting, you can say it is getting reduced, and as the metal is getting reduced, pure metal is forming a coating on that cathode. So after you can say after a prolonged electrolysis, after a prolonged electrolytic refining, we get to see that this rod is actually formed of the pure metal. It is actually, you can say, no other impurities are present, and all those impurities which were present with the impure metal just settle under anode as anode mud. So this is how we refine metals. So we have already over that the metallurgical steps. That is, first the zero step which I consider was the grinding of the ore. We already did. The second was the concentration of ore. We already did with hydraulic washing, with froth flotation, with magnetic separation, with leaching process, right? The second metallurgical process was the conversion of that concentrated ore into a metal oxide. We already did with calcination or roasting. You know that, in which we were heating the ore in absence or the presence of air, right? And you have to keep in mind this, that roasting is used for sulfide ore, and for carbonate ores calcination is used, right? And it is just a method to get rid of the fraction of the volatile fraction. The third step was like after getting the metal oxide, the third step was to convert the metal oxide into metal and oxygen. That means we need to employ certain kind of methods in which we get to separate the metal and oxygen, right? Because we are concerned with the metal, not with the oxygen, right? So what we'll do is, I told you that we'll employ different steps depending upon the reactivities of the metals. We did heating, we did smelting, we did electrolytic reduction. So you know that how to reduce the metal oxide. And after reducing, our motor is not solved, because actually we are looking for ready to use form of metal, right? So we'll employ the fourth step, that is the refining, and as I told you that depending upon the properties of the metal and the impurities, we can just separate them out by using distillation, liquation, zone refining, electrolytic refining. So there are many more other methods. So I've just employed these four methods. One method is just striking in my mind, I want to discuss with you, that is polling, right? Polling is also one of the method of refining. So what actually in polling, like polling is employed where you can say there is a metal oxide which like there is an impurity present in the mixture as metal oxide. So what you do, you just take it on a hearth, that is the metal impurity mixture, you heat it and then you stir it with the log of wood. So what happened, that actually by stirring you succeed in converting the metal oxide back into the metal, and the oxygen that is removed, that is released actually, if some impurities are present, it is capable of oxidizing that impurities. So again in that procedure also we get rid of all those impurities, and as a result we get the metal. So this was our metallurgical process which was to be taken into consideration during the isolation of elements. I think you got it in a proper manner. Now what to do is just to like as I taught you in different steps, so just sum up those steps, get familiar with those steps, concentrate on the figures, and also keep in the mind the limitations. That is the very important part, because if you are not aware of the limitation, you won't be able to choose a perfect step for a perfect metal, right? So you need to be you need to take care for all that things, right? So this is what was the metallurgy.